Okay, so, oh rats, the reflection, for the little camera, the reflection is right where these numbers are. And it's sort of where those numbers are. I just have to add these up. So this is 78, 108, 113. It's still too big. Okay, I'm just trying to come up with an example. So this is 37, 21, 15, let's say 14, what's this? 58, 68, 73, 83, 87, okay, 87, 90, 100, and then let's say P6 is 10. Is that just 100? Yeah, that's 128. P7 is also 10 out of 128. And P8 is 8 out of 128. If somebody wants, can you just quickly add those up? Okay, wait, there are messages in the chat. What am I doing? I'm just writing some numbers. So these should add up to 128. If somebody wants to check that and let me know, that would be great. Today, Huffman coding, 118, really drat. In that case, I'm just going to add, this is 9, so, okay, P9 equals, so I dropped it from 8 to 9, so it was 119, and then I'm going to have another 9 over 128. Okay, so that should be better. Is the first one is 37. Okay, so I'm going to change this back to an 8. Okay, P8 equals 8 out of 128. Okay, so today we're going to talk about Huffman's algorithm. Now, I stayed up writing an extra proof, adding an extra proof to the chapter, so I didn't get enough sleep, so I'm a little bit out of it, which is normal for me. Okay, so before we get into Huffman coding, I have to tell you a little bit about information theory. So when we started the course, and I was saying, I'm just going to check that this is recorded. And I asked for things, what has computer science accomplished that's comparable with everything is made of atoms, or the Earth goes around the sun, species rise, blah, blah, blah. And somebody suggested information theory, which is pretty deep. I don't really consider it computer science. I consider it electrical engineering. I think Shannon considered it electrical engineering. It's a little bit fuzzy because, for example, my first PhD supervisor, he got his degree from MIT, where Shannon was, and where all this stuff was happening. And officially, he was an electrical engineer, but he was a cryptographer, and he couldn't do anything like electrical engineering. But that was what it was called. So what is information theory? Okay. So before Shannon, this paper, Shannon published this paper, a mathematical theory of communication, which is now generally referred to as the mathematical theory of communication, in 1948, in I think the Bell Systems Technical Journal or something like that, which was top notch. And so before that, there wasn't really a way for people to talk about information scientifically. I mean, you couldn't really measure it. I mean, how do you measure information? in such a way that you can talk about it as scientists, like seriously. And I think still, even now, people like to think about information as somehow having meaning, as being important stuff. If I tell you if I tell you what the weather's like, that's not so much information as if I tell you that there's going to be an asteroid strike tomorrow. Now, actually, okay, so if I tell you something surprising about the weather, like lightning struck the same place twice, you're like, yeah, who cares? But maybe that's as unlikely as an asteroid strike. So actually, even if the probabilities are the same, you'd be like, yeah, well, I care about this one thing and I don't care about this. I care about this and I don't care about this. So the thing I care about somehow has more information for me. Let's forget that, okay? So we forget the meaning. We forget all the semantics and the consequences and the importance and the societal impacts and stuff like that of what this information is. It's just we consider that there's going to be some message and we have to transmit it precisely faithfully. Our job as electrical engineers, as computer scientists, is to get the message across. It's not to worry about what the message is about or what it will be used for or anything like that. We're just, we're doing communications. Somebody gives us a message, we just send it or store it in such a way that we can recover it. Now, there is lossy, oh, I have to start the timer. There is lossy compression, like MP3s and stuff like that. Okay, so I'm going to I'm going to change this, and I'm going to change this to 20 minutes because maybe I've been talking for 5 minutes. Okay, wait, here, I can look and see. So I've been talking for 18 minutes. Yeah, okay. Start. Okay, so for example, MP3s. You have data compression there, you get fantastic compression with MP3s, MP4s, but the problem is they're actually throwing away a lot of information. Right? So it's not actually data compression, it's data reduction. And they do this by, you have this psychoacoustic model of the ear, so they know that the human beings can't actually tell if two sounds are very close together, which one preceded which one. So they actually get rid of that. The problem is you have to have this and you can't tell differences in volume when they're very, very small, and certain loud noises will mask soft noises. And so they get rid of a lot of information. The problem is you have to have this psychoacoustic model of the ear. And like, who wants to do that? We want to do computer science. We don't want to do like psychoacoustics. This is disgusting. I spent 3 years of my life in a psychology department, and I want those back. We're not going to worry about this noisy stuff, this lossy compression, where you have to worry about, what value, what do you want to lose, what tolerance do you have. Forget that. We're going to worry about noiseless. So this idea is just somebody says, I want to send this is the universe of possible messages, right? And we don't care what those messages are. We just want to assign a code to those so that when somebody comes and says, okay, well, it was actually that. So you have a random variable, right? So Shannon said, like, if we forget what the messages are, what they mean, and we just consider that we're going to stand here and somebody's going to come and tell us how an event turned out. Right? So there's this random variable. It's going to take on values according to a certain probability distribution, which we know, which is p equals p1 through pn, say. So it's a discrete probability distribution. And with the person at the other end of the communication channel, we've worked out a code where somebody comes and tells us, what value the random variable took on. We're supposed to transmit that value according to the code. And we want to choose this code so as to minimize the expected number of bits we need to send. Now the code is supposed to be something called self-delimiting. So that means that every code word, when the person at the other end gets to the end of the code word, they know they're at the end of the code word. So sometimes this is called prefix-free because it means that none of our code words can be a prefix of any of the other code words, because if they were, then the person at the other end, when they get to the end of the code word, which is a prefix of another, they don't know if the code word is if they've seen that or if they've seen just the start of this longer code word. Okay. So for example, it would be bad if I had a code word that was 00110 and I had another code word which was 0011011. Right? Because if I send this message to the person at the other end of the line and they say 00110, they don't know if now they can stop or if they have to wait and get 2 more bits. Okay, so this, we don't want to have this. So instead, we want to design this prefix-free code. And Shannon said, okay, we look at the probability, we forget what the messages are. We just look at this probability distribution and we try to figure out what is the minimum expected code word length. So if somebody gives us a probability distribution, say P1 through P8, so these are just positive, so let's ignore the things with probability 0. So these are positive numbers that sum to 1, okay? And this is all we're going to work. We're going to build the code according to this. We're going to build one of these prefix-free codes. Now, in the notes I go through, Shannon said, okay, so information is the opposite of uncertainty. So how do we measure information? Well, it's how do you measure uncertainty, and it's the unit you use for us is a bit, which stands for binary digit. It was actually suggested to him apparently by Tukey, who was either Cooley or Tukey. It was one of the guys who rediscovered the fast Fourier transform. And a bit is your uncertainty about the outcome of a fair coin flip. So if you have an event and it's 50% one outcome and 50% another, and before this happens, your uncertainty about that is 1 bit. Right? So what is your uncertainty about the roll of a 6-sided die? It's actually, it's more than 2 bits, because you can express any of these outcomes with you can't express all of the 6 outcomes with 2 bits, but you can with 3. So it's something between 2 and 3. It's actually log base 26. Okay, so this is not an information theory course. I stuck into the notes Shannon's axioms of uncertainty, and then so the main thing for us, 20 minutes have passed already, well, 15. So for us, the important thing is this problem of building a code given a probability distribution, okay? Shannon came up with this thing called the noiseless coding theorem, which said you have a measure on any probability distribution. So if P equals P1 through Pn, then you have this measure called H of P, the entropy, which is, well, a lot of people electrical engineers tend to put the minus sign out in front. We just flip the fraction in the log. So this is Pi log pi. So he showed that he gave these axioms of uncertainty, saying like, okay, if all the probabilities are uniform, then the uncertainty increases as the number of possibilities increase. And if you break the events up in a certain way, then you know the uncertainty has to be the uncertainty of the first part plus the uncertainty of the weighted uncertainty of the second part. Blah blah blah. It's in the course notes. So he showed that entropy. This is the only function that fits in the ML class. Oh yeah, but read the notes. See if I present it nicer. So I used to do this stuff way back when, like 20 years ago. I was into, actually I'm still on the data compression program committee of the data compression conference. I do compressed data structures. So I do data structures and data compression mixed. So these are sort of I couldn't decide which one I liked more. So my take on stuff is different from machine learning though. Okay, so notice I haven't put a subscript on the log. That's because changing the base of the log changes the constant, right? And right, so if this is log 2 or log 10 or log base e, then it just changes everything by a constant, and that changes the units you're working in. So if it's log base 2, you're working in bits. If it's log base e, you're working in this weird unit that the electrical engineers like called nats, because it's the natural logarithm. Right? Okay. So you have this, and Shannon said, okay, you can't beat this. So the first part of the noiseless coding theorem, the lower bound, says you can't design a prefix-free code which has expected code word length less than this. Okay, so I'm going to put log because we're going to consider we're going to consider binary codes and we're going to consider bits. So he said you can't design a binary code where the expected code word length is less than this. What is the expected code word length? Well, it means that I design the code and then one of these events happens, chosen according to this probability distribution. Well, if my code words have length L1 to Ln, in this case 8, my expected code word length is sum over pi Li. Right? So I send Li bits with probability pi. Okay? So he said you can't beat this, and actually if we have time at the end, the proof of that, a rough proof of that, is in the lecture notes. That's what I stayed up and added last night. And if we have time at the end, I can sketch it. It's pretty easy, the lower bound. But it's not actually necessary for an algorithms course. And he showed that you can get to within 1 bit of this. You can get an expected, a code with expected code word length, and well, actually strictly less than the entropy plus 1. So let's just quickly go through that. Watching to make sure this doesn't, 7 minutes, 12 seconds, okay. So what he did, he said, suppose, so I had to write these, I couldn't just come up with arbitrary number because I wanted them to be in order. Because Shannon said, okay, without loss of generality, suppose you sort the probabilities. Suppose the probabilities are sorted. Okay. So what he did, he said, let SI equals sum j equals 1 to I minus 1. Can you read this at all? No. Okay, I'll write it a bit bigger. So we have these PIs. You could read those because you were working out what the numbers were. So we have SI equals sum j equals 1 to I minus 1 of pj. Is this better? Yes, okay. So, the key property here is, and we view this as a number, right? It is a number. It's the sum of a bunch of probabilities. So it's a number between 0 and 1. So actually S1 is exactly 0. Okay? Because it's the sum from j equals 1 to 1 minus 1, which is 0, of pj, so it's an empty sum. Okay? So what, so here we have S1 equals 0. S2 equals 37 over 128. S3 equals 58 over 128. This should be familiar because people just worked this out for me. Equals 73 over 128. S5 equals plus 14, 87 over 128. S6 equals 100 over 128. S7 equals 110. Wait. Right. Oh, I have two 10s. Good. S7 is plus the first 10 over 128. And S8 equals 120 over 128. So the last thing, if we added the 8, we would get 1. Okay? Now, the trick Shannon used was he viewed these as binary numbers. Okay? So, binary fractions. So before I write these out, to give you this example, so notice that if you take two binary fractions, these are just like decimal fractions like 0.37125. Okay, before we get into the binary stuff, imagine that two numbers, 37125, something, something, something. So this is x, and this is y. Okay, I tell you that these two numbers agree on their first 1, 2, 3, 4, 5, their first 5 digits after the decimal point, to the right of the decimal point. Okay? Then, what can you tell me? So I tell you that x and y agree on their first 5. I tell you that x is less than or equal to y. What can you tell me about y minus x? You can say it's less than what? I'm waiting, watching the chat. Actually, while you're thinking, I could restart the little camera because it's been 25 minutes. Why? Yes, but specifically related to the number, the fact that these are five digits. I mean, is it possible that these two differ by like a 1/10? So, okay, I'll restart this in just a second. But notice that the most y can be, so the smallest amount x can be is if this is followed by a whole string of zeros, right? If the part I didn't tell you, it's all zeros. And here you say, okay, well, how big can that be? Well, maybe it's followed by a whole string of 9s, but no, it's not. Because if you have 5999999 for infinity, then you don't write 5999999. You write 6000000, right? So y is actually less than this 599. So the difference is at most, is actually the difference, y minus x is less than 0.1, which is equal to 0.000000111111999999 minus 0.0000. So it's less than this minus this, because this is bigger than y can be. This is as small as x can be, and that is exactly 1, 2, 3, 4, 5, 10 to the minus 5. Okay, reset. And I'm going to change this to 25. And restart this.